Okay guys, in our last video we introduced this concept of a geometric sequence, or these sequences that are constantly multiplying by the same value over and over and over again. In this video we're going to look at kind of writing rules for these geometric sequences. And so, like arithmetic sequences, geometric sequences are very, very well behaved. And that is to say that if you wanted to know the value of any given term, it's kind of easier to find because all we would really need is the value of our first term here, a1, and we would also need to know what it is that we're multiplying by, every time to get to the next possible term. So our value of our common ratio, or the value of r here. So to kind of put together a pattern here, let's say that, my first term, I know my first term is my first term, but what if I wanted to get to my second term? As far as I'm aware, if we were to look at how this sequence works, we're starting at the first term, we're going on to the second term here by multiplying by r. So if that's the case, then to get to the value of the second term, the way I look at this is we're going to take a1 and we're going to take it times r. Now, if we wanted to get to the third term in our sequence here, let's take a look at our third term. This would be a3. And the way I kind of look at this is, again, if we know the value of the first term here and we know what we're multiplying by every time, then to get to the value of the third term, we would just take the value of our first term again, but we would have to multiply by r twice. And so I'm going to write a1, and this can be written as times r, but a little bit more succinctly, we can write this as a1 times r twice, or a1 times r squared. Let's go ahead and build in one more term here to kind of see if we can pick up on a pattern here. If I wanted to find the value of my fourth term, we could certainly start at the value of my first term, so take a1 and multiply it by r, but this time we'd have to do it 3 times to get from the first to the fourth term here. So times, and this would be times r third. So the idea is, if I were to write a rule for the nth term, how might this be done? In every possible instance, we're always starting with the value of our first term, and we're multiplying by r, but you'll notice here that the number of times we multiply by r, respectively, is always one less than the position we're in. And the reason why, just to remind ourselves here, is, for instance, in this fourth term value instance, we have to go from the first to the fourth term with respect to taking the first number and multiplying by r. But we're only going to have to multiply by r 3 times to hop across these gaps to get from the first to the fourth term. So in general, we're going to say we're always going to multiply this a1 times r one less times than the spot or the position that it's in. So this right here, as a matter of fact, this is our rule for the nth term of a geometric sequence. And we're going to be using this to write some geometric sequences. So go ahead and highlight this. You definitely want to highlight this guy right here. This is going to be important. This is as important to us as was the rule for writing the nth term of an arithmetic sequence. So looking at its parts, we have 4 parts here. an, which is kind of our output, right? Our term value. We say this is the representation of the value of the nth term. On the right side, we have a1, which is representing the value of the first term. R is our common ratio, so what we're multiplying a1 by from term to term. And then we notice that n represents the value of the term's position. So in this a sub n here, n represents the position of the term we're finding, and also corresponds to this n over here in the function itself. Okay. So one thing I'm going to throw out there really, really quickly is that this is our rule for a geometric sequence. What if I were to write the rule for an arithmetic and we did a little bit of compare and contrast? So arithmetic rule for an nth term, this is an equals a1 plus d times n minus 1. You can see that these are very similar in that we're always starting with the first term. In this sequence up here, we're adding on a common difference every time. In this sequence down here, we're multiplying on a common ratio every time. And each of these contains an n minus 1, albeit a little bit differently in the geometric sequence because it plays more of an exponential role than it does up here where it's right next to our d and we can distribute. So looking at this, let's go ahead and write a needs list here. Basically what this means is if we're going to write any geometric sequence, there's 2 things we need in every sequence, the first term and what we're multiplying by every time. So we need a1 and we need the value of r. These are the 2 things that we're always going to need here. So let's kind of take a look at maybe writing some rules for some of these geometric sequences and also some of the things we should and shouldn't do as we do it. So the instructions here say write the rule for the nth term of the following geometric sequences. So as we look at this, we see that we have our rule for the nth term. The value of any given term is the first term times r, 1 less times than the position we're in. So as we look at this letter A, you're going to notice that we have the sequence itself. As a matter of fact, you might recognize this from one of our first pages here. And immediately I recognize that what's happening here is I'm multiplying each term by a third to get to the next successive term. So In that case, I suppose that would mean that our R value is 1/3, and we could always go and check this here by taking any given term like 9 and dividing by the term before it, like 9/27. I suppose we would get 9/27. We would get 1/3. Okay. The other part of this that we need is our A1, and I can see easily here that the value of A1 is 27 here. So we have the values of R and A1. As far as writing the rule goes, let's go ahead and give ourselves some space here. We're going to say the nth term is equal to the value of the first term, so 27 times R, which I'll substitute that in, R, 1/3, okay, right here. And this is to the n minus 1. We just put this right here, and the neat thing is I'm going to put a kind of a, I normally put a box around it, but I'm going to designate this. This is our rule. And now, unlike where we have to, when we write the rule of an arithmetic sequence, distribute the d and combine like terms with a1 and the negative d here, this is something where I am unable to multiply 27 by 1/3. So let's go ahead and make sure we list something over here for at least this first given rule. We're going to list ourselves a never here. One thing we're never going to do. Never call this an equals 27 times 1/3 is 1/3 of 27 is 9 to the n minus 1. These two things are not the same. So why am I saying this? Because in this entire expression up here, the fact that we have an exponent is always going to need to happen first before we're allowed to do this multiplication here, just because of our order of operations. So when it comes to writing geometric rules, one thing has to be said about it. It's much faster than writing arithmetic rules because you only need to substitute in the values of A1 and R, and you're done. One thing I would like to have you try, or at least make sure you do, is make sure you test your rules. So if I'm going to do a quick test here, what if I wanted to find the value of, say, A2, since I know it's supposed to be this 9 right here? I would get 27 times 1/3 to the, and this is a 2 minus 1. So in other words, I get 27 times 1/3 to the 2 minus 1 is 1, and 27 times 1/3 is 9. That means that the value of A2 is 9, and that's certainly what we're supposed to get here. So taking a look at these next two examples, they're worth mentioning just because in the first example we have the sequence and roster notation. Well, letter B here, we just already have the two values we need, A1 and R. So in terms of writing the rule, there's not much we have to do else here other than just say, look, we started with the term value of 6, and our R value is a -2. So let me write that a little bit more cleanly. And this would be to the n minus 1. This would be our rule here. And honestly, we would be done. And just to check this out here, if we had to write a few terms of this sequence, our first term is 6. We're multiplying it by a -2, so we get -12, +24, -48. For instance, if my fourth term here has a value of 4, we might check it. A4 would be equal to, using this rule here, 6 as an initial value times 2 to the 4 minus 1, which becomes 6 times -2 to the 3. And -2 to the 3, which we have to do first because of our order of operations, -8. We get a -48 here, which is, I'm happy to see, is what we do have as our value of our fourth term. So the last possible example here, we're going to look at a bacteria colony, which we know is something that grows exponentially. So it says a bacteria colony has an initial population of 4 bacteria. The bacteria triple every hour. Write a rule that describes the population of bacteria AN at any given hour n. So one thing I want to encourage you to do is, at least with story problems, really look at the time here, the time, which was in hours, okay, and then the number of bacteria. Look at this as a situation where we're kind of looking at what's happening here. So initially at time 1 here we have 4 bacteria, but what's happening every hour? Well, it's tripling. So in the second hour, if I triple this 4 here, I'm going to get 12, and I can even write in my rate of change here. So if I triple this again in the next hour, I'm going to have 36, and we'll do one more tripling here, times 3. This would be 90 plus 18 is 108 during the 4th hour. You can see that this is just going to continue here. Excuse me. So with respect to what we need to know, remember, we need to know A1 and we need to know R. In this particular verbal problem here, our A1 is kind of like our initial value here. So we have 4 bacteria, and our R pertains to this growth or decay rate, in this case a growth rate by a factor of 3. So because we have these two values here, suppose we can write a rule, and with respect to this rule, we'd say A1 equals, I started with 4, and every hour, fix my 4 a little bit here. It's tripling, and this is to the n minus 1. I've got to tell you that this right now is already the rule that describes the situation. Now, one thing I want to mention is the reason why I did ask you to make a table for these word problems is a little bit easier to see what is this rule actually doing for us. So it's kind of saying, as long as I know the time in hours, which is my n here, okay, so give me the time, then what I would be able to tell you is the number of bacteria, and that would be our output, A sub n. So for instance, if you were studying this and you said, man, how many bacteria should I expect to have in the 8th hour? We could say, well, my rule is A sub n equals 4 times 3 to the n minus 1. So if we did 8th hour, we would have 4 times 3 to the, I suppose, 8 minus 1 power, which is 4 times 3 to the 7th. And I'm going to need to use my calculator here. Let's turn this on. 4 times 3 to the power of 7. My calculator is going to do the exponent first and then quadruple it here, but we get 8748. We can wrap our heads around this just because this is an exponential progression here. But 8,748 bacteria in the 8th hour would be phenomenal growth. But then again, this is some exponential function. This started with 4 or something and is tripling every hour, so it should grow rather fast. Cheers.